Hi everyone. In the lecture of today, we're going to introduce the so-called generalized linear models. And the particular kind of generalized linear model we are going to examine today is logistic regression. So, if you think of all the examples we've seen so far in this course where we applied some sort of linear regression model, be it like simple linear regression, multiple linear regression, or even regression including random effects, so-called linear mixed models, you will notice that there was one thing that all of these examples so far had in common, namely that we always fitted models with certain particular assumptions. The main one being that the dependent variable, not the predictor necessarily, but the dependent variable, reading times or whatnot, psychological symptoms, that this was always a continuous variable. Okay? And we always assumed that there was some sort of linear relationship between the predictor or possible multiple predictors, aka independent variables, and our continuous dv. Further, we always assumed implicitly that the residual errors, like basically the distances from between the observed and the predicted y data, that those would be normally distributed. And that's, we can get very far with that as long as, these assumptions are met, which is usually the case when we have a dependent variable whose residuals, are more or less normally distributed. And even if they aren't, as we saw last week, we can sometimes apply a transformation, which will make the residuals sort of more akin to being normally distributed. Like for reading times, for example, we would usually apply the log transform or the inverse transform. So that all still falls under this like general category of models of like linear regression models we've seen so far. But now comes the new thing. So now think of research questions, which we might have, where our dependent variables are actually categorical, not continuous. Okay? Several examples. Say you're running an experiment where participants have to memorize and then later recall words. Okay? So what you might want to measure is, for each observation, is whether a word was or wasn't recalled correctly by a participant. And then you might have some information about the words that you included in your experiment as well. You might, for example, track their frequency overall in language. And say your research question was that, or like, if the frequency of a word has an impact on how likely it is to be recalled correctly. In that case, you would have a dependent variable, which is categorical, because it is the recall basically, which can be either correct or incorrect. So that's a categorical binary variable, unlike the kinds of DVs we've seen so far, which are continuous, like response times or psychological symptom scores or whatnot. Okay, so that's a categorical DV. Another example, let's say you're doing a sort of sociological survey of students at Uni Potsdam, and you're trying to find out whether the socioeconomic status of a student, however you quantify that exactly, has an effect on how likely a student is to live either on campus in Golm or in Berlin or in Potsdam. So now your DV would be the location of residence with three levels: campus, Berlin, or Potsdam. And that is what you basically are interested in now as the outcome, right? And what you want to potentially find an effect on. Or third example, say you're running an experiment with grammaticality judgments, like where participants have to look at sentences, read them, and then judge how grammatical they are according to them. And this you can do, for example, with the Likert scale. So if you think of a somewhat gradual notion of grammaticality, you might give people a scale with 5 response options, saying like, I completely reject the sentence, I don't find it grammatical at all, or I find it a bit weird, I'm not sure, I think it's acceptable, or I'm confident very much that it's acceptable. Like 5 different levels, that are ordered in a certain way. That could be your response options you provide to the participant, well, a so-called Likert scale. And that could be your DV, like the responses on this like 5 response option variable, basically. And you might have some hypothesis about certain predictors of the response behavior. Let's say, for example, the native language of the participant. Maybe people with some native language will judge like English sentences in a different way than people from another native language, assuming you're just like comparing L2 speakers, okay? So non-native speakers. In that case, you would have a DV, again, categorical, 5 levels. The only difference that now they have like some order. Okay, so as we saw in these examples, we wouldn't be able to use the linear regression models we've seen so far because all of them would assume that we have a continuous variable whose residuals are normally distributed. But here, as we can clearly see, we have categorical variables, which we could even like subcategorize in 3 different kinds. So binomial variables would be those where we have exactly 2 levels, okay? Multinomials, those where we have more than 2 levels, so 3 or more, for example, Berlin, Potsdam, or campus, the place of residency. And ordinal categorical variables would be the ones where the levels have some intrinsic order, okay? So Likert scales are a classical example when we have something like how often do you smoke question, and that's the variable, and you have 3 response options, never, sometimes, or always. That would be an ordinal variable because we have, this inherent order of the response options on a Likert scale, let's say, for grammaticality judgments or something like that. But, in all cases that look like this, where, the DV is not continuous but categorical, we have to go beyond the kinds of models we've seen so far. We will need a so-called generalized linear model, okay? So the generalized linear model is basically an extension of the linear modeling framework we've seen so far, which allows us to ask precisely these kinds of questions that we've seen above when the DV is categorical. And within this framework of generalized linear models, there are different variants. The most notable ones that you might come across at some point in your research and statistics career will be logistic regression. That's the one that we're going to focus on today and in this course in general. But there is also beta regression, Poisson regression, or gamma regression. Like all of these are variants of the generalized linear modeling framework. And basically, all of them can also be extended to a mixed model framework. Like when we have hierarchical repeated measures data, then we can use a logistic regression, for example, which also includes random effects. Like all of them can also be used in such a way. In order to familiarize ourselves with the basic concepts and ideas of logistic regression, it might help to look at a concrete data set where such an analysis would actually apply. Such dataset is the Beetle dataset. The Beetle dataset is from a study by Dobson 2008, and it basically reports or summarizes the results of a biological experiment, I guess, where people were studying some kind of beetle, so some kind of insect, and particularly how they react to a certain poisonous gas like carbon disulfide, okay, to which they were exposed over a duration of 5 hours, and there were different subgroups in the experiment, and between those groups the dose of that gas was varied. Okay, so kind of a sad experiment, like beetles died. Okay, but that's how it is. And we have the data set here, which looks like this. So we have these 3 most important columns here, or actually the only columns, I guess, where dose is like a numerical variable, a predictor in this case, which tells us how big the dose of that poisonous gas was. And then we have the number of beetles in that particular condition. So you can think of, some beetles had the 1.69 dose, some had the 1.72 dose, and so on. So this is basically how many beetles were exposed to which kind of dose, right? And then you have the column killed, which is the number of beetles out of the overall number of beetles in that particular sort of condition, which died as a result of that exposure to this poisonous gas. Okay, so you can read, for example, this as like in this condition where there was this 1.69 dose, whatever that is, like micrograms, milligrams, I don't know. There were 59 beetles and 6 of them died. And for that condition with the 1.72 dose, there were 60 beetles and 13 died. And as you go up, you can already kind of descriptively see a trend that, you know, the proportion of beetles killed gets higher with the dose getting higher. So here you had 62 beetles exposed to 1.86 quantities of that poisonous gas, and here almost all of them, except for one, died as a result. Okay, so got killed basically. So the research question here would be, does dose affect the probability of killing the beetles, like those insects? The first thing we could do, like descriptively, would be to calculate the proportions of beetles killed per sort of level of dose, okay? So we could do that by, creating a new column in our data set called proportion, like number dead beetles, okay, prop n dead, and we can give it the result of computing the number of killed beetles divided by the number of overall beetles in that particular dose level, like dose condition, okay? And if we now look at our data set again, after extending it by such a column, we can now see that we indeed have this additional information now, and we see that, well, here for that condition, for that dose value of 1.69, we have 10% of beetles killed, so 0.10 roughly, and then here we have 21% beetles killed, and for the higher dosages, we see that also the proportion of killed beetles becomes larger, right? So here we have 82% of the beetles killed with 1.81 gas quantity, and for that highest dose, we even have like 100% of beetles in that condition that died as a result of that exposure, okay? So we can also summarize the numbers that these proportions give us, okay, and see that, you know, the median, the maximum and the minimum proportion across those different dose conditions. What we also might want to do is to create a plot where we have on the x-axis the dose, like ranging from the values included in the dataset, so 1.69 up until 1.8 something, and on the y-axis precisely those proportions of beetles killed, just to get like an overview of how the deadliness of that gas exposure increases as a result of increasing the dose. And we can see indeed that there's some relationship here. So we start with relatively few beetles being killed proportionally with low doses, but for the high doses it's very clear that it's lethal for almost all of them, okay? So that's descriptive information we can get out of this data set. Note that the y-axis, by definition, has to be bounded here between 0 and 1, right? Because these are now proportions, so there can only be the minimum proportion of 0 or the maximum proportion of 1, meaning 100%. Like there's no values above or below that range. That's an important property here. Now, if we want to approach this naively, we could try to kind of fit a linear model to this data set. We'll see in a moment why it's a bad idea, but in principle we could try to do that, okay? There's nothing stopping us from doing that. So if we wanted to approach this, you know, with the tools we have so far, like linear models, we could say, okay, let's look at this plot. I can try to find the best fitting line here, right? So why not just do that? I mean, isn't that a good idea? So we could, you know, take our predictor, the dose or the center dose, depending on if I want to center it or not. And I can run a model which has this dose like as a predictor and the proportion of killed beetles as the outcome variable. And I might get a summary of that gives me an intercept and a slope, right? So summarized here, like the intercept and the slope of that best fitting line. And I could think, yeah, okay, that's a possible way to analyze this data, right, statistically. That's certainly looks like I get a reasonable result. You know, there's a trend that I'm representing with this linear model. Isn't that okay? Isn't that fine to do? So there are several reasons why this kind of simple linear model analysis is not the correct analysis in this case. One reason being that the relationship between the predictor and the outcome, the probability basically of dying, is not linear. It usually has this S shape, so something like this you would see if you plot the proportions of either outcome. So that you can kind of see this here, even if it's not like a very strong trend, but you can see that this general S shape that you would expect here is also applying here. And it's kind of a sketchy thing to try to fit a linear line to an outcome that you already, by its properties, assume to actually have this kind of S shape. Okay, so that's one reason why it's not really the appropriate analysis. Another reason is that the predictions may reach outside these bounds of the y-axis, which can only be between 0 and 1. So while the data itself, like the killed or not getting killed, or like the summary proportions of that, can only range between 0 and 1, the predictions might go beyond that conceptually constrained interval. So you might see, for example, here that the predictions here, they go beyond the 1, actually, even though the 1 is really the maximum possible value for that y-axis here, right, for proportions of deaths, okay? And likewise, they can go beyond the 0, which is also not conceptually sensible. In addition, the confidence intervals, they can range outside of the 0 or 1 bounds, even if the estimate itself is inside them. So that's another problem. In addition, linear models would usually assume normal distributions of the residuals. Here, the errors, if you think not of the proportions now, but like actually of the underlying dependent variable, right, which is a 0 or 1 variable, like 1 being killed and 0 being like not killed, okay? These are like the underlying data points, okay? Forget about the proportions for a moment, but these are like the actual binary categorical data points underlying here. And so for a continuous dependent variable, like the kinds we've seen so far in this course, we have like this entire range of values that they can take, for example, reading times or whatever. So they could be ranging on this entire scale of numerical values, okay? And here it makes sense to quantify continuous normally distributed residual error, because if that's like the mean and some data points lie here and some lie here, then okay, you can compute the residual, and it might be some real number like minus 0.5 or 1.2 or whatever. But if your dependent variable has not like this continuous scale, but just two discrete possible values, then what you actually have to consider to be the error can only be a 1 or a 0, okay? Meaning that if your model predicts that the outcome should have been killed, but the observed outcome is not killed, then the error is 1, okay? Because there is a 1 difference between 0 and 1. Or alternatively, if your model predicts that the beetle should have been killed in that particular observation, and it was indeed killed, in that case the error is 0, right? So the error can only take two possible values underlyingly, okay? Which is either 1 or 0. And that is not at all compatible with the assumptions of a linear model, where you assume the residuals to be normally distributed, to have these continuous normally distributed values, right? A related point is that linear models would assume constant variances, meaning that no matter where I am exactly on my scale of my dependent variable, the linear model would assume that the variance around the value, the predicted value, would be always the same, right? No matter whether I'm here or here or here, the variance would stay constant. But we can clearly see here with these proportions of deaths that that is not the case. Meaning that if we are here somewhere in the middle, okay, we can have some variance, But if we are at a dose with 100% deaths, there has to be zero variance, because if I allow that there is variance, then I'm again outside of the bounds of my 1 to 0 interval, right? Which is the only interval on which the proportions are defined. So the variance gets smaller at the edges. Like if I'm close to dose with 100% deaths, I have very small variance, or even like zero variance at exactly 100%. And likewise, the same for a case with 0% deaths. Here also I can't have any variance, so I have 0% variance, and so the variance will depend on where I am on this sort of scale of the dying or not dying variable, okay? And that is another thing where data, like an example of data like this, is not following the assumptions that a regular linear model would have. So in summary, due to all these reasons, we can see that we cannot use the linear regression model, or the linear mixed effects regression model, the regular kind we've seen so far, in order to tackle this problem and analyze this data. So what is the alternative? Well, I mean, okay, we have seen that the proportions of beetles killed, or we can also think of them as probabilities, right? The probability of beetles getting killed, that those are not in a linear relationship with our predictor, the dose, okay? But there are actually functions of that probability which transform it into something new, like into a new kind of quantity, which then is actually linearly related to such a predictor, like the dose, for example. Okay? And one such function is the so-called logit function. So once we are looking at logits rather than just probabilities, we are suddenly in a situation where we can, in fact, make the assumption that some numerical predictor, or even potentially categorical predictor, has a linear effect on that outcome. Not in probabilities anymore, but in so-called logits. Okay, we'll see in a moment what logits are. But so the general conceptual idea is that we will still predict the probability in a way of my outcome, let's say beetle getting killed or not getting killed. But instead of modeling it directly, we're modeling it indirectly through this so-called link function. So the logit function is such a link function. And a link function is the function of the mean of a dependent variable at some point. For example, if I'm at dose 1.7, then I get the mean of my ones and zeros, and that will be 0.2, which would correspond to a probability of 20%, let's say. So it's a function of the mean of the dependent variable at some particular point on my predictor. And we're now trying to model the outcome of that link function, in this case the logit function, okay? So this will enable us to model our dependent variable again as a linear function of our predictor, and we can then estimate the beta parameters just as we would do for the regular linear regression, like the intercept and the slope. And once we've done this, then we can generate predictions, which will be in logits, so not in probabilities, but in logits. But we can back transform those predictions, if we like, into actual probability scale in order to make them more interpretable. So how does this transformation that this function does work? Well, it computes the so-called log odds, which are my logits. Okay, what are odds? What are log odds? That's what we're going to look at now. So when I have a probability, which is a value, between 0 and 1, or like between 0 and 100% equivalently, I can compute the odds based on that probability by using this equation here. So I can take the probability, for example, 20% or 50% or 60% or whatever, and so represented as a value between 0 and 1, so 0.6 or 0.2 or something like that. And I would compute the probability divided by 1 minus the probability. Okay? That will give me what is called odds, which is actually a quantity that's quite intuitive for us. So if we have a probability of 25%, let's say, so p is equal to 0.25, then we could compute the corresponding the odds accordingly by saying, okay, the odds will be equal to 0.25 divided by 1 minus 0.25, so 0.75, and this will give me 1/3, okay? So the way to read this is, okay, the odds are like 1 against 3. So if I have 25% probability, my odds, intuitively, how we know that word also from casual language, my odds are 1 against 3 to find that outcome. Like in one case, I'll get the outcome I'm talking about, and in the remaining 3 cases, I will get a different outcome. That's how you can literally read the odds. Or if we take like the other example where we have a probability higher than 1/2, we could have probability being 75%. In that case, the odds are 0.75 divided by 0.25, and this will be 3. And you can also write 3 as a fraction. Okay, so you could write 3 divided by 1, even though that's kind of a redundant thing to do, but you could write it like that. And then you can read this directly in this same format again. So you could say my chances of getting the outcome I'm talking about are 3 against 1. So in 3 cases, of 4 cases, I'll get my outcome, and in 1 case, I won't get it. Okay, that's how you can basically think of odds intuitively, and always there's like one unique odds value associated with a specific probability value. So it's sort of another way, a different way to express a probability, right, on a different kind of scale. So that's what the odds are, and as a next step, we can take the logarithm of the odds, and that will give us the so-called log odds, okay? Why do we want to use log odds? Like, why is that interesting for us? Because, well, first and foremost, log odds can be assumed to be more or less normally distributed, okay? They can, in principle, range from -infinity to +infinity, like any other continuous variable that is normally distributed. And it also will help us to make the interpretation of the output of a model easier. In what precise way, we'll see in a moment once we start seeing logistic regression outputs, okay? Right, so here's another example of, odds and log odds. You take a probability, say 0.87, and you compute 1 minus that probability, like in the example here, and that would give you, in this case, 0.13, and then you can compute the odds by taking the original probability p divided by 1 minus p, what's called q here, and so this would be a value in odds, and taking the logarithm of that will give you the log odds, which in this case is 1.9 something, okay? And now, so the log odds are at the core of the logistic regression equation. So here we see that the equation of our logistic regression model looks like this, where on the left side of the equation we have precisely the formula for computing log odds. So this is p divided by 1 minus p is the odds term, and then the logarithm of that gives us the log odds. And this is now expressed as equal to beta 0, the intercept, plus beta 1 times our predictor variable, in this case, dose, right, for that beetle dataset. And so this model is the logistic regression model, and as we discussed, the dependent variable here now is actually a transformation of the probabilities, these proportions, into this log odds scale, basically. And so the aim of the modeling is just like for linear regression, we want to find the optimal beta values here, the beta parameters for intercept and potentially one or many slopes. And one thing that we should take into account here, though, is that the estimation of the betas will work in a somewhat different way from what we're used to in linear regression. So like our classical method of least squares estimation, which we could use for linear regression, won't really apply here, okay? So we'll have to use a different way to estimate the betas. And the thing is that once we've estimated our beta 0 and beta 1, we can then, if we want, move back from the log odds space in which the result will be expressed to the probability space using, simple math, simple algebra. So let's say we had a logistic regression model like that. So log odds is equal to beta 0 plus beta 1 times the dose. Then we can use math. We can exponentiate both sides. So take e to the power of each term on each side, right? So if we exponentiate an expression of a logarithm, this will just cancel out the logarithm. So this will give us p divided by 1 minus p, the odds basically. And on the right side, we now have exponential of beta 0 plus beta 1 times the dose. And this equation, we could now just solve for p. And once we do that, we will get an expression like this. So p is equal to this division here, where we have exponential of beta 0 plus beta 1 times dose divided by 1 plus exponential of beta 0 plus 1 plus beta 1 times dose. Okay, so by computing this, knowing what our beta 0s and beta 1s are and what our specific value for the dose is, we can basically calculate the probability that corresponds to that particular value, the predicted probability in a sense, right? So that is the mathematical theory. Now let's see concretely how we can fit a logistic regression model in R. So staying with our example of the Beatles dataset, let's fit a model in R. And the way to do this will be to use the GLM function, that stands for Generalized Linear Model, as opposed to just LM, okay? And we will now give it the proportions of dead beetles as the dependent variable, okay? And those will be our predictor. But now, importantly, we'll have to specify a couple of things. So we'll have to say family equals binomial. That is the specification we have to make for a logistic regression, because the relation is that binomial means we have an outcome variable that's categorical with two values, right? So 0 or 1, that's a binomial variable. And we give it the data, okay? And this is also important. We'll have to specify weights, and weights will give this this value from the number column in our data set, which, recall, if we go all the way up to the summary of our data set, the number tells me how many observations there were for that particular level of dose, okay? And so it's roughly 60 observations per dose level, but not exactly. So in some cases I have like 59, in some cases I have 62. So I should consider how many observations I had for every particular possible level of dose in my data set, and then weight sort of the regression by the number of observations. So if I had like 100 observations in a certain level of dose, this proportion I can compute from 100 observations will be more reliable, right, than the proportion I could compute from just, let's say, 5 or 10 observations. So that's why we will also have to specify the sort of weighting in the generalized linear regression call, and we will need to give it a column like this, which basically tells us, the amount of observations that there were in each level of my predictor dose, for example. Okay. So going back to the R call of the generalized linear regression, so that's what we're going to do, and we can save this now as we usually do in some variable. And before we look at the summary, a few further remarks about this function call. So here we just wrote binomial. We could also have written binomial and then logit, or like link equals logit, which would be a bit more specific in telling this function call that we're using these log odds, aka logits, as our link function. But that's also the default link function for the binomial attribute here. So we can just leave it out, and by default it will assume logits. Then there are also two ways in which we could run logistic regression. So one would be what we are seeing here. So we are basically providing it as a dependent variable, this proportion, together with the argument weights, which tells us how many observations there were for each level, so that it can basically reconstruct, okay, if I have a proportion of 0.7 and there were 100 observations, that basically is equivalent to saying I had 70 observations with 1, let's say, and 30 observations with 0 not killed. I could also, if my data set looks a bit different, if I provide it in the so-called long format, where I have in each row one observation with like either 1 or 0 and not these like summary statistics with just the proportions. In that case, I would specify it like this. So GLM and then dead, which would be then a variable just containing zeros and ones, not proportions, but really just discrete values 0 or 1. And then I wouldn't give it this weights argument. If my data were in that format, then I would call the function like this, but the result would be equivalent. But given that here my data set already summarizes the mean sort of proportion, or like the proportion of deaths for each dose level, I will call it like that here, and then specify this weights argument. So these are some variations of the logistic regression, but the idea overall is all the same. So looking at the output here, we can again use our summary function as we usually do, and we'll get an output that looks very familiar to what we also used from the linear regression. And so the interesting thing here is, of course, the effect of dose, where we see that there is an estimate, and this estimate is expressed as a difference in logits, a difference in log odds of 34. Okay, it's a bit hard to understand what that means in terms of difference in probabilities, okay, but here the interesting thing is, of course, to see if that's making a significant having a significant impact. And indeed we see that the dose has indeed a huge impact on the probability of beetles dying, which we also kind of intuitively saw by looking at the summary statistics, where we saw that there is this trend, right? That's also confirmed here by our logistic regression model. We could plot this outcome as follows. So we could plot the predicted values like this. So what we could do is, okay, first just do the same plot as we saw before, where we just show the proportions of deaths, for each included level of dose. And on top of that plot, so that was the plot, right? The circles here are the observed descriptive proportions. And on top of that, we can now also plot the predicted proportions, okay? And this line of code will achieve this for us. So we'll do points, okay? And then specify FM1, which is our model, fitted till the dose, and we will give it, the data set that this was about, the beetle data set, and specify what kind of shape the points will have, in this case this X shape. And so this is basically resulting in these X's, which are the predicted proportions, to be plotted on top of the observed descriptive proportions. So you can see that the X's, they mostly match what we see descriptively as well. And importantly, these are basically now our sort of the equivalent of the best fitting line from the linear regression, but for logistic regression. Okay, so as you can see, these predicted values, they are not in a straight line. They are also sort of S-shaped, which kind of respects what we expect to see with such proportions and probabilities in a logistic regression scenario, right? So that's basically now the result. Okay, so at this point you might be asking yourself, but how can I interpret the intercept and slope estimates I get out of this logistic regression meaningfully? Okay, so let's have a look at that. So we had the summary here. We saw that there's a significant intercept, whatever that means here. We'll see that in a moment. And we have this significant effective dose, and we get these estimates associated with them. They have a standard error. They have a z value now, not a t value in this hypothesis test in the regression model. That's very typical for the logistic regression, that you have this z and not t value, but it's almost kind of similar to interpret, as you get above a z value of 2, you will have a p value which is significant, which is less than 0.05 roughly. Okay, but what do these mean? Minus 60.7 logits for the intercept and 34 logits for the slope. How can we interpret this meaningfully? Let's start with the intercept. So the intercept is basically representing the log odds, which correspond to the probability of being killed, of a beetle being killed, when the dose is equal to 0. Okay? If we had centered dose here, which in this last model that we just fit we didn't, but if we had centered it, then it would mean the probability of being killed at the average dose, okay? But here, like look at the function call, here we gave it the original dose values, which are not centered. In this case, the intercept will correspond to the hypothetical probability of getting killed when the dose is equal to 0, right? And the way we would reconstruct this would be to reconstruct the corresponding probability would be to back transform this log odds value to probabilities, which we can do by using this formula here. So we could say the probability will be equal to exponentiating this log odds value beta 0, or b0 being like the estimate for beta 0, divided by 1 plus the exponential of b0 again. And so this will give us the probability which corresponds to the intercept, which again is sort of this hypothetical probability of getting killed when the dose was exactly 0, which is quite far off from the actual dose values from like 1.7 to 1.8 or 1.9 that are actually in the data set. And so the way to do this is, we can do this in R, like just write this mathematical formula down in R, and as a result we'll get this probability, which is basically 0, right? It's a number with order of magnitude of 10 to the power of minus 27, so like a 0 point and then 26 zeros and then a 4. So it's like a very tiny probability, right? Which in a way makes sense because, I mean, if this is like your sensible range of doses, and then this is between 1.7 and 1.9, and then you go all the way to the left up until you get to the hypothetical dose of 0, that's of course a point where the probability of this S-shaped logistic regression pattern is already basically zeroing in on the 0 almost, right? So it won't be exactly 0, but it will be a tiny probability because we didn't center the predictor. So it's not a very meaningful result, but that's how you would interpret the intercept in this case where we have an uncentered predictor for the logistic regression. Okay, if you didn't have the time to actually compute the corresponding probability using this back transformation formula, you can also use this general rule of thumb basically, or actually a fact, not a rule of thumb, which is that if my logits value is negative, then this corresponds to a probability of less than 0.5, less than 50%. If my logit value is positive, then this corresponds to a probability of greater than 0.5, right? And if my logit value is exactly 0, this corresponds to a probability of exactly 0.5. Talking about this intercept now, this basic probability that's represented by the intercept. And we can see here, this was minus 60. So that means that, it's negative, clearly. It's not positive, it's minus something. So that means that already seeing this sign here, we can basically tell that, that the probability we'll get out is actually smaller than 0.5. And indeed, as we see, it's actually even dramatically smaller than 0.5. It's almost 0, right? But it's not bigger than 0.5. Another way to do this calculation here with this exponential divided by 1 plus the exponential would be to use the R inbuilt function plogis. I'm not sure how to pronounce it. But anyway, you can just give it your logit value and it will do precisely this computation for you, to back transform this into a P probability, okay? And this will give you the same result here. All right, that's the intercept. Now, what about the estimate for the slope? So B1, our estimate for the slope, recall that was 34, okay? That is representing a difference in log odds, okay? So it tells us how much the log odds change with an increase in the predictor X dose of exactly 1 unit. Now, this being a difference in log odds corresponds in the odds space to a ratio, right? If you have some ratio and you take the logarithm of that, then this will be a difference in logarithmic space. But if you exponentiate again, that difference becomes a ratio again, right? And so that's also the relationship between the log odds and the odds scales. So differences in the log odds scales correspond to ratios in the odds scale. We can make this estimate now somewhat more intuitive by thinking of it as a ratio in odds, a so-called odds ratio, literally, as opposed to a difference in log odds. So let's exponentiate our estimate here, and this will give us the odds ratio as a result. So what we see when we do this is that we get this huge number as a result, which is actually roughly 764 trillion. Okay, that is our odds ratio here. Now, that might strike you as somewhat implausibly enormous. Let us unpack why in this case we end up with this really huge odds ratio. Okay, so remember that we are talking about by how much the probability of a beetle dying or not dying is affected by a 1 unit change on the predictor variable, in this case our predictor dose, okay? And 1 unit on the predictor on dose is actually a very huge step, okay? Because recall that our actual data, like if we go up and see what the range of our actual data was, it was just between 1.7 and 1.9. Like that's sort of the plausible range of possible doses you can vary where all the action happens, and where like with 1.7 almost no beetle was dying, and with 1.9 almost every beetle was dead. And we're now asking the model to give us a slope which represents going up by 1 entire unit on this scale of dose. So that's understandably very large, and that's why also our odds ratio here turns out to be something like really big, because it's not about like plausible or pragmatically relevant amount of change in the dose, but about this hypothetical really large change in the dose. So that would represent the increase in odds, like by a factor, going, for example, from an original dose of 1.7 to a new dose of 2.7, like way outside of our range, or let's say a dose of 0.8 to a dose of 1.8, like below, way from outside of our range into our range, okay? So that is why this odds ratio, if if really looked at as a number, as an odds ratio, that is like a bit a bit large, so 764 trillion. So that is why our odds ratio, if interpreted at face value, is that gigantic in this case. So let us like quickly try to understand how to read this. It would basically mean that if our original odds of beetle dying were 1 against 2, which could be represented like a fraction, 1 over 2, 1 divided by 2, then an increase in dose of 1 unit would correspond to increase in the odds of what is a multiplication of our original odds by that 764 trillion. So 1/2 times 764 trillion, so we would have about 380 trillion as our new odds basically of a beetle dying once we've increased the dose by 1 step, 1 entire step. Or like another example, if your original odds was 2 against 1, which you could represent as a fraction as 2 divided by 1, which is just 2, then it would mean, okay, if you now increase the dose from where you were by 1 step up, in that case your odds, which originally was 2 against 1, would now be 1.5 quadrillion to 1, okay, because you've now multiplied your original odds 2 by that 764 trillion odds ratio. All right? So this is how we can read and interpret the slope estimates. Like once we've converted them from differences between log odds to odds ratios, we can interpret them as basically this factor by which we have to multiply our original odds in order to get the new odds, which represent the new odds after going up 1 step on the predictor variable. Right. And lastly, we have a small question here. So what would have happened if we had centered the dose predictor? What would have changed or not changed in our output and in its interpretation? You can maybe think about it for a moment and pause the video if you like. Okay, so the answer would be that just as for linear regression, the intercept would have been the thing to mostly change. So the intercept would then represent the log odds, which corresponds to a probability, for dying under the average dose as opposed to dose equal to 0. Because once we center dose, then the new 0 on that centered predictor scale would represent the average dose, right? And the intercept will always correspond to the value for when our predictor is equal to 0, whether that means the dose being 0, as in the original scale, or the dose being the average dose, as in the scale that we get after centering. The slope should stay the same, it shouldn't be affected. It could be that numerically it might not come out exactly the same, but at least in principle the slope is not subject to change mathematically depending on whether we center the predictor or don't center it. All right, so we now basically know how to read the intercept and slope estimates from a logistic regression model. Now, with that knowledge, we might start to think about how we can generate predictions from an already fitted logistic regression model. So we now have our model, which is, we have fitted it to the data. And now let's say we want to predict if the probability of a beetle dying if I give it a dose of, let's say, 1.7552, okay? So in order to do this, we can create for ourselves like a small design matrix, X, just as we learned it for like the matrix formulation of the regression model and so on, and then multiply this with our matrix containing the beta estimates. And this design matrix will just contain one data point. So I want to create a matrix basically which has as the first, so one row because one data point, and the first value will be 1 for the intercept. That's always what I have for the intercept column. And the second value will be the value of my predictor dose, so 1.7552. And so this will be my design matrix X in this case. And I also know what my beta estimates are, so they will be in my beta matrix or like beta head matrix, which will be, what was it here? The intercept was minus 60 and the slope was 30. So this beta matrix is containing the values minus 60, roughly, okay, or minus 60.7 and 34, okay, in one column. And so what I want to do is to multiply this X matrix with that beta matrix. This will basically do the multiplication of 1 times the intercept plus 1.75 times the slope, right? That's what the matrix multiplication X times beta hat will do for me. I can do this in R. So I can create this design matrix using S matrix and giving it this vector. Now by default, this vector, if I transform it into a matrix, will be a column vector. So like one column, but 2 rows. But actually we want for X the opposite. We want 1 row but 2 columns. So in order to get from here to here, we'll do the transpose. So this transpose of this X is actually our design matrix X here, okay? And we can matrix multiply this with my matrix containing the beta coefficients, which I can get by doing coef, like coefficient of my model object. And once I do this, I get the predicted log odds for that particular value of dose as a result. So what is the result? It is minus 0.566 log odds, okay? So the log odds of dying under a dose of 1.7552 is minus 0.566. You could convert this into a probability using the formula we saw above. Intuitively, you can already see it will be a probability that's somewhat less than 50%, right? Because the log odds are negative. If the log odds were positive, it would correspond to a probability larger than 50%. Alternatively, if we don't like matrices, we can also compute it somewhat more manually, okay, or like using more simple algebra. So we could extract B0, the intercept, and B1, the slope estimate, And we can then compute the predicted y value, like the predicted log odds, by like writing down our regression formula, which is beta 0 plus beta 1, or b0 plus b1 times the value of dose we are interested in. And this will give us the exact same result of minus 0.566 log odds, as we also saw above. And we can change this value back to probabilities, as I just said. So we can apply this formula, exponentiate the log odds, and divide it by 1 plus the exponentiation of the log odds, and we see the probability, which is 0.36, so 36%. In other words, the model predicts that under a dose of 1.7552, there is a 36% chance of dying for a beetle, okay? All right, so the next topic relating to logistic regression would be confidence intervals. Okay, so assuming that the log odds have a distribution that's approximately normal, which usually is the case, that's why we can use them sort of. We can also compute the confidence interval around the log odds estimate. For example, for the log odds of death given the dose of 1.7552. So okay, we have that probability, right, 36%, but we want to know how much the uncertainty around the probability is, and that uncertainty can be computed on the log odds scale again. And so one way to express this uncertainty is through the standard error. Now, the way to compute the standard error here would be the following. So we could first extract the variance-covariance matrix of our intercept and slope estimates from our already fitted logistic regression model. So that's what we are doing here, and we're saving it in a variable called vcov_mat. Okay, so here we can see the variance-covariance matrix. And now we can compute the standard error by running the following matrix multiplication. So we will take the design matrix, in this case our little small design matrix for just this particular data point for the dose, okay, so 1.7552, and we're going to multiply the design matrix with the variance-covariance matrix and then the transpose of the design matrix, okay? So here I'm just renaming our design matrix like in the form we needed, which is this like one row, two column form. So design M is literally this X here. And then we can do design matrix multiplied with the variance-covariance matrix multiplied with the transpose of the design matrix. And the result will be a 1-by-1 matrix, which as its single element will contain the standard error squared. Okay, so the standard error we're looking for is basically in the result, only that here we have the square of the standard error. So as a next step, we might want to compute the square root of this result here, of the 0.0216, and what we will then get is indeed the standard error for this estimate, okay? So based on the standard error, we can now compute the boundaries of our confidence interval. The way to do this would be to say, okay, we have our original log odds, which recall were the following. So we had generated that prediction, right? So minus 0.566 log odds, which corresponded to a probability of 36%. So that's our log odds. And we now want to know basically how much uncertainty there is around that estimate. So we have the standard error now, and we can say our log odds minus 1.96 times the standard error. That will be our lower boundary for the confidence interval. And likewise, our log odds plus 1.96 times the standard error, that will be our upper bound for that confidence interval. Right, just recall that for a Z distribution, which is what's underlying the logistic regression here, the quantiles at which, like within their range, there is a 95% probability mass is precisely from the mean of the normal distribution minus 1.96 standard deviations up until the mean of the normal distribution plus 1.96 standard deviations. That's where this particular number comes from. It's the particular number we will need in order to get 95% confidence intervals. Okay, so the result we get for the limits of the confidence interval in this case would be minus 0.85 expressed in log odds for the lower limit, and minus 0.2776 for the upper limit. What we could also do now is to convert each of the two limits into probability scale again. So we could do that by applying our usual formula, right? So, I mean, first of all, we can see the same result as before again, which is just converting our original predicted log odds into probabilities. That was 36%, right? And now the idea is to just apply the same sort of logic, the same sort of formula to our lower and upper limit of the confidence interval. So by doing that, we'll get a lower limit on the probability scale of 29.8% probability and an upper limit of 43.1% probability. So overall, we know now that for our specific dose in question, namely 1.7552, there is a predicted probability of 36% of the beetle dying with an uncertainty around it, expressed as a 95% confidence interval, going from 29.8% probability to 43.1% probability. Right? Next, let us clarify a few little things regarding the mathematical notation that we can use regarding logistic regression. So think of the linear regression case for a moment, like all the linear models we've seen so far, where we could write b0 plus b1x, for example, for simple linear regression as the mathematical term representing our prediction, okay? So what we could write for linear regression is to write that the expected value e of our random variable y, if we think of our outcome data as sort of a random variable, given x, like conditional on having some specific predictor data available, that will be equal to, well, exactly beta 0 plus beta 1 times x for a simple linear regression. Now, the analogous thing in logistic regression would be the following. It would be to write, so as opposed to writing expected value e of y given x, we will typically just write pi of x, where pi sort of stands for probability, okay? And the logic is the same, so it's sort of the predicted outcome expressed in probabilities. And as we saw before, the predicted probability pi of x can be represented by this mathematical term here, so the exponential of our beta 0 plus beta 1x divided by 1 plus the exponential of that, okay? And if we solve this mathematical formula for beta 0 plus beta 1x, we will get this as a result, right? So the logit function that we've seen also previously. So logarithm of the probability, the predicted probability divided by 1 minus the predicted probability. That is, you know, our log odds, aka logits, and this we can think of as a function g of x. And this g of x is precisely what we call our link function here for logistic regression. All right. So what about errors in logistic regression? Recall that the logistic regression model is constrained to predict probabilities in the interval from 0 to 1. It can therefore not have a residual error term of the kind that we know from linear regression, which could be normally distributed, because that would make predictions of the probabilities go outside this range, all right? So there are no residuals, no residual errors in the sense that we knew from linear regression in the logistic regression case. In the logistic regression model, each observation, y, can be either 0 or 1, right? So each observation, that would be a specific beetle either surviving or dying, 0 or 1. And what is assumed here is that those observations of either 0 or 1 follow a so-called Bernoulli distribution with a mean parameter, aka a probability, conditional on the predictor values that we have for dose, for example, or for the intercept. And this means that for any value of my predictor x, dose, let's say, there are two possible errors. So if my observed value of the beetle dying or not dying is 1, which I guess could be the beetle being killed, dying, then the error would be equal to 1 minus the predicted probability. Okay? And if my observation instead was 0, so if y is 0, that means the beetle survived, then the error is equal to 0 minus the predicted probability, or just, you could write this as just minus the predicted probability. So this is how we can compute and speak of errors in logistic regression, but in general, as you see, this is a bit different from the kinds of residual errors we've seen before in linear regression. And just a quick example of how to compute such an error concretely. So let's say we have our predicted probability for a beetle being killed with a dose of 1.772, which, as we established before, is 36%. Now, let's say we have a beetle A, which receives this dose, 1.772, and it dies. Okay, that is represented by the outcome 1. Then the error we have here is 1 minus the predicted probability, so 0.64. And alternatively, if we have a beetle B, which received that very same dose, 1.772, but it did not die, like it survived, that's the outcome 0, then the error will be 0 minus the predicted probability. So 0 minus 0.36, which will give us minus 0.36. That is the error in this case. Okay, so next there is this concept called deviance. The deviance of a model, for example, a logistic regression model, tells us something about the distance between the predicted values and the observed values. Like in this case, the predicted probabilities and the observed 1 versus 0 outcomes. And the smaller the deviance, the better the goodness of fit. So goodness of fit is sort of a concept that says if my deviance is low, then I have a high goodness of fit, meaning that my predictions match my observed values very much. The deviance as a numerical metric can be obtained by comparing the log likelihood of a saturated model, that is a model which has as many parameters as there are data points, to the log likelihood of our fitted model, that is a model, for example, with an intercept and one or more predictors. Now, this term saturated model, you have to think of it sort of as, well, if a model has as many parameters as there are data points, then it will be always able to fit the data perfectly. Okay, so there will be no difference between predictions and observations if I have as many parameters as data points, they can vary freely. That is the key property of a saturated model. It's sort of a useless model because it will always fit data perfectly and it doesn't abstract from the specific data that it sees. So in that sense, if you think about what the deviance of the saturated model itself is, well, trivially it is obviously very low. Like it's good in the sense that there is no deviance, there's zero deviance at all, but that model is probably not useful, okay? Now, the deviance has or follows a chi-square distribution with the degrees of freedom parameter of that chi-square distribution set to n minus p, where n here is the number of data points and p the number of parameters. We're going to see some examples to make this a bit more concrete, right? But just as a last little note here, you'll often also see the term residual deviance when describing the deviance of a particular model of interest, like the model with an intercept and a predictor or more predictors. The reason being that, as we said, the deviance always describes the difference in goodness of fit between the saturated model, which would predict the data perfectly, and our actual model. So in a sense, the deviance is also something like an error, so like the overall residual error, the residual deviance, which basically quantifies how much variation in the data remains unexplained by the model. So that's why we also sometimes see this called residual deviance, right? So let's see this concept of deviance in action in our concrete example dataset and corresponding logistic regression model regarding the beetle data. So recall that the deviance is a value, a number, that can be assumed to be sampled from a chi-square distribution. And the chi-square distribution is a probability distribution which we can also use to conduct significance tests, as we saw, for example, for the likelihood ratio test. Now, what would it mean to conduct a significance test on the deviance of a model? Well, let's say we define a threshold like 0.05 and we look up on the corresponding chi-square distribution if our given deviance value corresponds to probability of less than 0.05, like if it's that extreme. If that is the case, if we have like a very large deviance and we see that the corresponding probability mass right to it on the chi-square distribution is less than 0.05, then we could say that our model is not adequate. Like if we find a significant situation, then we would basically say our deviance is so large that it's not good anymore. Like the model is not adequate. The goodness of fit is not given, right? That could be the conclusion here. So let's see what would happen if we first fit a null model, which just includes the intercept, but not our predictor, which is dose, right? So we can fit such a null model using the GLM function, and we will just write 1 as opposed to dose here, where we typically write our predictors. And we specify the usual things like binomial, that's our type of regression model we want to fit, which stands for logistic regression. We give it the weights argument and we give it the data. And then we can compute the deviance by just running the command or the function deviance and give it as an argument our fitted logistic regression model. Now, the deviance here is 284.2, right? So what we could do now is we could look up the critical value of the chi-square distribution that corresponds to this, which in this case would be 7 degrees of freedom, because we have a number of data points minus number of parameters in that model would give us 7. And we get as a result 14. So that is the value that if it is surpassed, our p-value will be smaller than 0.05, meaning our model is not adequate. And what do we see? Well, we see that indeed our deviance here being 284 is way above the critical value, which is 14. So 284 is much bigger than 14. Therefore, we can conclude that our null model has a deviance that is too high, like it does not have sufficient goodness of fit, right? Which is, understandable because it doesn't include that very crucial predictor dose. Now, consider the model which does include dose as the predictor, the one that we've basically fitted earlier already. Here we can do the same spiel again. So we first fit the model, we compute the deviance. The deviance is 11.23. And now we see, okay, that deviance is less than the corresponding critical value. The critical value has changed a little bit because now we are looking it up on the chi-square distribution with degrees of freedom 6 as opposed to 7. The reason being that we've now added one parameter being the slope parameter here. But still, the 11 that we get out of the deviance computation here is still smaller than the critical value. That means that our p-value would be above 0.05, and that means that our model seems to be adequate. Like it is adequate enough that the deviance does not seem too big here in this significance test on the deviance value. In the example we just saw, we would typically call the deviance of the null model, that is the model that only included the intercept but not our predictor of interest, the null deviance. And we would typically call the deviance of our full model, that is the model that did also include our predictor of interest, the residual deviance. Now, the interesting thing is that using those deviance values from the null model and the full model, we can also conduct hypothesis tests on the difference between those two deviances. The idea being that we want to find out whether adding our predictor of interest into the model significantly decreases the deviance, aka increases the goodness of fit, or not. And so the fact that we can exploit to do this is that even differences between deviances follow a chi-square distribution. Not only deviances themselves, but also differences between deviances. And the corresponding degrees of freedom that we need when we look at a difference between two deviances, for example, the difference between the deviance of the residual, or like the alternative model and the null model, would be P minus Q, where Q is the number of parameters in the null model and P is the number of parameters in the full model, okay? Or the alternative model, as I just called it. So how can we do this here in our example? So in our example, we would want to evaluate whether the dose has an effect that is, significantly improving the goodness of fit of the model. So first, we have our null model fitted, right? Its deviance was 284 on 7 degrees of freedom. And we also had our alternative fitted, whose deviance, aka the residual deviance, was 11.2 on 6 degrees of freedom. Now, before we get to the actual computation of the significance test on the difference between deviances, let's maybe first have like a visual intuition of how good or how bad the predictions of each model are, the null and the full model. Okay, so here we have the predictions of the null model. These are these small x's here. And because there is no slope, you will see that they are just on a straight horizontal line. Like no matter what the dose is, which is actually called log concentration here, but that's just our dose from 1.7 to 1.9, it will always be the same because there's no predicted dose yet, so it will just sort of try to estimate the average probability of a beetle dying or not dying throughout the entire data set. And here those small circles, these are our actual data. So you can see that the predictions are not so good, right? Because the actual data has this S shape, but our predictions are now just this flat line for the null model. Likewise, for the full model, we see this plot that we had seen at some earlier point in the lecture as well, where now we have these x's here, which are our predictions, and we have those circles, which are still our observed data. And now we see that these predictions are actually much better, much closer to the real data here, visualized as those proportions, like aggregate proportions for particular values of the dose. So just intuitively, we already see visually that this is a much better goodness of fit than this, but let's actually try to verify this using the significance test we can do on the difference between deviances. So we saw the deviance for the null model, 284. If we subtract from it the deviance on the full model, 11, then we end up with a difference between deviances of 273, which will now be on 1 degree of freedom, because that's the difference in the number of parameters from the null model compared to the full model. There is one added parameter, the slope. And what we can do now is we can look at the chi-square distribution that corresponds to this, so the chi-square distribution with degrees of freedom 1, and find the corresponding critical value for a significance threshold of 0.05, and that is 3.84. So we can clearly see that comparing our actual observed difference in deviances, which is 273, to this critical value, that it far surpasses it. So this tells us that adding the slope predictor significantly increases the goodness of fit, or like decreases the deviance of the model. So we can be very confident, we can reject the null hypothesis that this slope of dose is equal to 0. It clearly is something else, okay? Now we can do this model comparison also using the ANOVA function. It's basically a sort of likelihood ratio test actually, right? So we can give the ANOVA function our null model and the alternative model. And as a result, we'll get the output here, analysis of the deviance table, where we see a summary of, well, that was the deviance of our null model. This is the deviance of our full model, and here we have the difference between deviances and the corresponding p-value, which is very, very small. So that tells us that adding this predictor does lead to a significant increase in goodness of fit. One variant of this, so you actually don't even have to specify both the null model and the full model. You can even give this ANOVA command just the full model in the case of these deviance tests here, and this will do the same thing. Like, it will automatically compute the null model for you and the deviance of the null model, and basically do the same thing now. So compute the difference in deviances here and give you the same output, the same p-value basically. So that's just another way of doing it, which saves you a little bit of typing, right? Okay, so that was all about deviance and how we can use it to run significance tests on adding a predictor into a logistic regression. Now, the last topic for today is multiple logistic regression. So just as for linear regression, we can also, where we can have more than one predictor, we can also have the same thing for logistic regression. And the example to illustrate this will be a data set from a psycholinguistic study on Hindi by Hussein and colleagues, 2015, where 10 participants had to read several Hindi sentences, each with several words, and we have a measure for every word of how long a participant was fixating that word. Now, here we're interested in understanding what factors impact whether a word was skipped, like not read at all, or not. This is an eye tracking study, so if you measure how long a word was fixated, it could also be that a word, here being some word, was skipped entirely and never fixated at all while the subject, the participant, was reading the sentence, right? So what we can do is we can effectively compute a skipping probability, that is the probability that a word is skipped, it was never actually fixated. In order to do this, we can create a vector that has the value 1 if the word has 0 milliseconds total fixation time, that is, it was never fixated, meaning it was skipped, and 0 otherwise, right? So that's the definition of the skipping probability. So we get an observation for a word, either it was skipped, 1, or it was not skipped, it was read at least a little bit more than 0 milliseconds. In that case, the value here is 0. So now, as you can see, we have precisely the kind of data that we need for a logistic regression. We have 1s and 0s for a particular observation, skipped or not skipped, just as we had 1s or 0s for the Beatles, killed or not killed, right? So this will be our dependent variable here. Now we will have two predictors, the word complexity and the word length. Each are sort of a numerical measure. And we will center both of them and then see how we can fit a logistic regression model that contains both of these predictors. So here's what the structure of this data set looks like. As you can see, there are a lot of different variables, a lot of different columns in the data set. For example, all of these, which are like caps lock abbreviations, are different kinds of measures you can extract from a reading study in eye tracking. But you also have, your usual information on which subject, like which participant a data point belongs to. You have the item number, you have the session number, trial number, a lot of different things. And what we can do here is to create this new column called skip, where we will basically construct our dependent variable of interest, which is the skipping probability. And the way we will do this is we're going to say that this skipping probability will have 1 as its value when the total fixation time on an observation was 0, that means it was skipped, and 0 otherwise. Okay, so that way we can create this new column in the data set, which will be what we want as our outcome. Now, as I said, we want to center our 2 predictor variables, word complexity, which you can see here, and word length, which you can see over here. So both of them are not centered yet, and we want to center them as predictors here for the upcoming analysis. So that's what these lines of code are effectively doing for us, like subtracting the average of a variable from the concrete values in each observation. And what we could do, which is not the correct analysis here, but just as a sort of proof of concept that we can in principle fit a logistic regression model, would be the following. So we could say, okay, we're just going to fit a logistic regression with skipping probability as the DV and word complexity and word length as the 2 predictors, using our usual specification of family and the data set here. Here we don't need to give it weights because here we have the data in the so-called long format, meaning that we don't have like summary proportions, but instead we have actual 1 and 0 values per observation in each row of the data set. That's why here we don't need that weights argument anymore. Now this will give you some output. You should just be careful though to start interpreting this and reporting this, because these were actually repeated measures data, right? So these were actually data where there were multiple observations per, let's say, participant, and that's why you can't, you're not allowed basically to run a simple logistic regression model that does not have random effects, because you're violating some assumptions of the model. So this analysis is incorrect. I mean, R is not stopping you from running it. You will get an output. That's the danger with R sometimes. But it is incorrect because, as I just said, we are violating some assumptions, in particular the assumption of the independence of each data point, which is not given if we have these like subgroups of data points, let's say by participant, okay? And this brings us directly to the last topic of today, which is the generalized linear mixed model. So a generalized linear model including random effects. This works just as we already know it from linear regression, from like non-generalized linear regression. We can, have by participant intercepts and also by participant slopes potentially. So how would we run such a mixed model for a logistic regression, let's say? So the way to do this is, very similar to what we already know from the linear mixed model case. We would use the glmer function as opposed to the glm function, and we would specify the formula of the model as we used to. And now we will also have this, if we want to add just random intercepts by subject, let's say, we will add +1 and then this vertical bar subject, that whole thing in brackets. That is, our Elmer syntax for by subject random intercepts. And we'll specify again family binomial, just as we did for the logistic regression without random effects. Give it the data set, and we can then run the model. Okay, one thing we had to do here as a very first step is to convert the subject column into a factor data type. That might or might not be necessary. It will happen either way, maybe if you run the model, but usually when you have a category like that, which you want to have as a basis for your random effects, it's a good idea to have it as a factor instead of just a vector of strings. All right, so we can look at the summary of this mixed model, and here we have our output for the fixed effects, what we are most interested in probably. So we can read different things of this summary, most notably that both the word complexity and the word length each seem to have significant effects on the skipping probability. Okay, we can see that in this automatic significance test output here, these p-values are clearly significant. They are below 0.05, let's say, so that tells us that, indeed these two factors had an effect. And based on these log odds estimates for the effect sizes, basically, we can also sort of see what the directionality of these effects are. So we can see by this minus on this logit, like difference between logits, difference between log odds here of 0.16, that as the word complexity increases, the skipping probability decreases. Okay, that's why we have a negative effect here. And likewise, as the word length increases, the skipping probability decreases. Or in other words, more complex words and longer words are less likely to be skipped, which kind of makes sense, right? I mean, if you have a complex and long word, you will most likely fixate it at least a little bit. Let's say you will not entirely skip it, but if you have an article like the, a, or a preposition like of, you might actually skip it entirely and just, process it a little bit parafoveally when you read a sentence. So that's the takeaway we can get from this model, and we'll also have our random effect summary now, where we can see this estimate of the variance of the intercept adjustments by subject, basically, just as we would also see that for the linear regression case. All right, that's everything for today. So we now know how to do not just linear regression, but like generalized linear regression, which is sort of an extension of that framework to cases where we don't have this simple, normally distributed, continuous DV, but for example, something like a probability or like binary outcomes, like 1, 0. And this is what we looked at specifically today. So that's the case where we would use logistic regression, which is one type of generalized linear regression, the only type we are going to cover in this course. And we saw how to apply it to a specific data set, both for the without random effects regression and for hierarchical data, where we had in fact to also include random effects. And we saw that this works just like we already basically are familiar with it from linear regression. All right, so I hope you guys enjoyed this week's material. Then see you next week in the next video lecture. Until then.